In this part, we'll look at Q function approximation. Q tables have limitations because they store the Q value of every state action pair. We'll look at two methods for representing Q tables more compactly: linear Q function approximation and deep Q function approximation. Both of these use machine learning to approximate Q functions. We'll compare and contrast these methods to each other and to Q tables, and we'll discuss their strengths and limitations. At the end of this section, you're expected to be able to apply linear Q function approximation to solve small-scale MDP problems, given some known features. You're expected to be able to select suitable features and design and implement Q function approximation techniques for model-free reinforcement learning techniques to solve medium-scale MDP problems. You're expected to be able to argue the strengths and weaknesses of different function approximation approaches, and to compare and contrast Q tables, linear Q learning, and deep Q learning. Let's get started. Using a Q table has two main limitations. First, it requires us to visit every state and select every action from that state many times to get a good estimate of the Q value of that state. Thus, if we never visit a state, we have no estimate of the action from that state, and if we never tried an action from a state, we have no estimate from that state. It also requires us to maintain a table that's the size of the state space multiplied by the size of the action space, which can be prohibitively large for any non-trivial problem. Let's have a look at the Freeway example here on the screen. In the Freeway example, recall that we have a kangaroo that we're trying to get from one side of the road to the other side without being run over by a car. If we abstract this problem a little bit, let's say there's 12 rows in the problem and around about perhaps 40 columns that the kangaroo can be in. That's an extreme underestimate because the kangaroos don't actually move a column at a time, they just move a few pixels at a time. But for now, let's just say that it's 12 by 40. That means there's 480 different positions that a kangaroo can be in. And there's two kangaroos, one here and one here. So we have to record the position of each of those kangaroos. And we also need to record the position of all the cars. Because we don't know how many cars there are at any particular point in time, the way to represent this would be to divide up our screen into the 480 different locations and have a Boolean variable that says true if there's a car there and false if there isn't. So from the perspective of a state space, we now have 480 different locations that a kangaroo can be in, squared, because there's two kangaroos, plus for the cars we have 2 to the 480 different combinations of where there's cars in each spot. If my calculations are correct, that would mean there is 3 times 10 to the power 147 different states in this MDP. Then we have to imagine that in each state, our kangaroo could go up, down, left or right. So there's 4 moves. So this would be 12 times 10 to the power 147 different entries in a Q table. Now remember, this is a huge underestimate because we've only modeled the position of the kangaroos and we've assumed there's only 12 rows and 40 columns, which is also an underestimate. So you can see here that storing this in a Q table becomes infeasible. We might have enough memory to store this, but we're certainly not going to sample this many actions, this many states in a reasonable amount of time. The key idea in function approximation is to approximate the Q function using other techniques such as machine learning. So for example, if we look at this problem, we know that if the kangaroo wants to get to the other side, the cars down in this region and the position of this kangaroo are largely irrelevant to the problem. If we can approximate the Q function on only the important parts of the state, we might be able to learn a lot quicker. We're going to look at two techniques for doing this: linear function approximation and deep function approximation, that use linear functions and deep neural networks in order to approximate our Q functions respectively. So how might function approximation work in an example like Freeway? Well, if we store in a Q table, remember we store the position of the kangaroos, and we might also have to store the position of the cars in order to know that we're not going to get run over if we move into a particular lane. However, when you think about making a decision from here, what are the relevant parts of the state that are needed to make this decision? Well, I would say there's only a few relevant parts of the state, and things like the car down here and the position of the other kangaroo are largely irrelevant. What's relevant is perhaps how far away we are from the goal, which direction the goal is in, and how close the cars are to the lanes that we're about to move into. So if we're evaluating going north here, what's important is if we go into this lane is how close is the nearest car that's driving along that lane, and how close is the nearest car in this lane as well. The nearest car in the lane below us here is not really relevant if we're going up. Maybe sometimes it is, but most of the time it won't be. We might also say that the actual position in the row is not that important as well. It's really just how far away the cars are that's important, so we could abstract that away altogether. So by just looking at, for example, how far away we are from the goal, where the cars are in the lanes above us and below us as we go to move, we're able to sort of look at our local environment in order to make probably very good decisions playing Freeway. It might not lead to absolutely optimal behavior, but I'd wager that we're going to learn this much quicker and much more effectively than if we tried to learn for every possible state. So first we're going to look at linear Q function approximation and how to represent Q functions using a linear combination of weights and features. The intuition in linear Q function approximation is that we no longer store the value of state action pairs, we store the weights of features in our environment, and we learn those weights using reinforcement learning. This has two main concepts. The first is a feature vector extractor FSA, which is a function that returns the values of the important features in the state that we have selected. This will be a vector of size n times a, where n is the number of features that we've selected and a is the number of actions that we have in our MDP. So fs as a extracts the value of a feature for the state action pair SA. We use the notation fi SA to extract the ith feature. The second important concept is the weight vector W, which is also of size n times a. The weight vector gives the weight or the importance for each one of these feature action pairs that we have in our problem. We use the notation WAI to refer to the weight of the pair that is the action A and the feature I. So, what we have so far is two concepts. A function that we have to write ourselves that will extract the value of the important features in our environment. For example, in Freeway, we would extract the distance of the car that's nearest to us in the row above us, the distance of the car that's nearest to us in the row below us, maybe how far away we are from the other side, whatever those important features we think are for that problem. We write a function that will extract those for each feature, and it will return a vector of these for us. The second thing we have is simply the weights for each of those features. This is the part we're going to learn using reinforcement learning. So we have the feature vector and we have the weight vector. How does this help us represent Q functions in reinforcement learning? Well, what we say is that for a Q function Q, the Q value of state action pair SA is simply the weighted sum of the feature values multiplied by their weights. So as you can see here, all we simply do is sum up for the n different features we take the feature value, such as how far away is the car in the row above us, and we multiply it by the weight. It's this weight part that we're going to learn using reinforcement learning. But why do we extract features as feature action pairs with the action as well? Why don't we just extract the state features? In the example I was talking about with Freeway, I discussed how far away the car is in the row above us, how far away we are. These are all properties of the state. Well, if we think about this, in the example here, when we're evaluating the decision whether to go up, left, right, or down, the values of features should have different weights. If I'm evaluating whether going up is a good action, how far away the car is in this row is more important than how far away the car is in this row. And similarly, if I'm evaluating going down, the distance of this car is more important than the car in this row. And similarly, if I'm judging going left or right, the distance of this car is more important than either of these two. So as we can see here that we extract feature action pairs because we want to learn different weights for these things. The different features have different weights depending on which action we're evaluating. A bit later, we're going to look at how we can define just state features and how we can systematically convert them into feature action pairs. So far, we've assumed that we have the weights of our linear function to approximate our Q values. But how do we actually learn these weights? We learn these weights by changing the update rule for our reinforcement learning algorithm. Instead of updating a Q table, we update the weights. So let's assume we're using an algorithm such as Q-learning or SASA. What we do is at the start, we assign the value of each of our weights to some arbitrary value. Let's say we're going to use 0 at the start, and I do recommend 0 at the start as a good way to interpret what's going on when you're trying to learn something. And we do this for every state action pair. So every feature and every action gets updated to A. Then we execute our reinforcement learning algorithm as normal, and we execute the action A in state S. We now have to do an update for that. Instead of updating the Q table, what we're going to do is we're going to update the weights. The rule for update looks like this. For each weight, I in 1 to n, we update the weight I for action A as follows. So the same as before, we've got a learning rate alpha, and we're going to weight new information alpha and old information 1 minus alpha. But it's the new information and how we use it that's different here. We've got our standard delta term here, which is, depending on whether you're using Q-learning or SASA or some other algorithm, is going to be the reward plus the future discounted reward. But now we multiply this by the value of our feature at state S for action A. So this would be, for example, how far away is a car in the row above us, or how far away we are from the goal, would be the value of that. This will update the weights, and if this was a positive action for feature I, it will update the weights in a positive way. If it's negative, it'll update in a negative way. Those of you who are familiar with machine learning might notice that this is very similar to doing gradient descent, except we're trying to maximize our function, which is our expected return, rather than minimize a loss function. So we're actually doing gradient ascent. We're trying to follow the gradient up. We'll talk more about gradients a bit later. So two important things to note here are that first, this is a much more compact representation of a Q function than using a Q table, at least when we have massive state spaces. We only have to store a weight vector, which is the number of features times the number of actions, rather than a Q table, which is the number of states times the number of actions. Typically, we're able to represent states using much fewer features than there are actual states. But a second thing to note is that this update rule has the effect of updating Q values of states that have never been visited before. So if we think about the freeway example, when we finally do cross the road and reach the other side of the road, we get some reward for doing that. That's the goal of the problem after all. But we will update the weight of our features for the action going up. And this will update the value of any state where we go up now for each of those features. So now by simply getting reward using one action, we update the weights for all of the features in that action, and therefore we update the Q values of all of the states for that action as well. So you can see that choosing the features is going to be very important for the problem. So now let's look at an example of updating weights in Freeway. We're just going to look at one of the features and one instance of it. But what we're going to look at is a feature that tells us how far away we are from the other side of the road. This is clearly an important feature because any actions that take us away from that won't have the same weight as actions that take us towards it. So let's assume this is feature number 6 in our feature action value pair. It could be any feature. And the feature has the value R divided by D, where R is the row that we're in and D is the number of rows that there are. This effectively normalizes this feature value to be a value between 0 and 1. And I do recommend that you normalize all of your feature values when you're doing linear Q learning, because it allows you to interpret a little bit more what's going on with different weights when all of your feature values are of the same magnitude. So we have our update rule, as we can see here, and we're doing Q learning because we're estimating the future discounted reward using the maximum value. Now let's assume that we reach the other side for the first time and we have to update the value of going up for, as I said, feature number 6. It's the first time we've done this, and let's say for now we've never been hit by a car, so we've received no negative reward, we've got lucky. We have to update this using the old value of the feature weight, which is going to be 0, plus our learning rate times this expression times the feature value. Now, I'm going to be very aggressive and say our learning value is going to be 0.5. I wouldn't really choose a learning rate that high, but let's say I did. We have to then multiply this by our reward. Let's say we get a reward of 10 for getting to the other side of the road in Freeway. I'm not sure what the reward is. 10 plus our gamma, for consistency I'll say 0.9 here, multiplied by the maximum value here, which we'll say is 0 again because we haven't got any reward yet, and minus the old value 0. But this is where the trick comes in linear Q learning, is that we then have to multiply our feature value by this expression. Now remember I said the feature value is the row that we're in divided by the total number of rows. If we've just gotten to the other side and we assume there's say 10 rows here, then it's going to be 10 over 10. So all we have to do now is calculate the sum of this expression, which is going to be 0.5 times so now the new weight of going up for feature 6 is going to be 5. When we calculate our Q value for going up in any state now, we're going to multiply the feature value by the weight. So as we go into our next episode, when we're trying to figure out what the Q value is for going up from state 1, we're going to multiply 1 over D, because this is our feature value here, times 5. That'll give us some weight that says that going up is a positive move, and that hopefully might help our multi-arm bandit algorithm to choose this when it's doing exploration. What our weights say here is that the closer we are to the other side of the road, the heavier the Q value is going to be for that state. Intuitively, that seems good to me, that we've got higher Q values for being closer to the other side of the road. So we've probably selected a good feature. So earlier on we talked about defining state action pairs as our features. And I discussed that often it's easier just to think about the world in state features and then convert them to state action features. Turns out there's a very straightforward way to do this. First, what we do is define our feature extractor where I is the name of the feature for our n different features. So we have a function that will extract the value of a state feature for a particular state. For example, how far away are we from the goal? How far away is the car in the row above us and the car in the row below us and the car in the current row as our features. At this point, we don't care about the actions. If we have this state feature extractor, it then becomes very easy to convert this to something that is n times a large as follows. We just define n times a different functions, feature I for action k, SA as follows. If the action is equal to action k, then we return the state value at that point. Otherwise, return 0. Now, for any of the features and any of the actions that are not feature I and action k, we simply return 0 in that part of the vector. And when the action is action k, we simply return the feature value. This effectively results in a different weight vectors, one for each of the actions. We can see here that we have one for state A1 that simply extracts the feature values, let's say 1 and 2 if we only had 2 feature values for that state, and otherwise returns 0 in the vector. And then for action 2 we have these two and 0 and 0, and for action 3 we have all of these 0 and we extract the feature values for these. The effect of this is that when we're calculating the Q value of action A1, we multiply the weights of all of the other actions by 0, and therefore these are completely discounted from the calculation. And similarly, if we're calculating the Q value of A2, the weights of actions A1 and A3 would be multiplied by 0 as feature values. So if we define our feature extractor here for our states, this is an automatic way to convert this to a feature extractor for state action pairs that will work for linear Q learning. Now let's compare linear Q function approximation to Q tables using our grid world example. We can see on the left here we've got the Q function represented as our Q table, and on the right here we've got our Q function represented using linear Q function approximation. The features that we've established here are the distance from the agent to the goal on the x-axis, normalized, the distance from the agent to the goal on the y-axis, normalized. These are both normalized by the maximum height and the maximum width, and also the Manhattan distance, so the distance of x plus the distance of y normalized. We can just execute one episode here. We can see the effect of Q function approximation immediately. Our Q table updates just one value, while for our linear Q function approximation, we can see that we've updated the value of the action up in every state based on our features. This update looks okay. We can see that at the bottom here, the Q value of this one is much weaker than this one because we're further away from our goal, and our feature extractor has extracted that distance. As we step through, we can see this pattern reoccurring after 5 episodes here. We've pretty much got some signal for all of our actions in our state space, but not for Q table representation. So if we step through it now, all the way to the end of just 20 episodes, we can see that we haven't yet got a very good approximation for our Q table, but using linear Q function approximation, we've already got a reasonable representation. If we followed this policy, we would choose one of these two actions. It's not a great choice. In this state here, we would choose right, also not a great choice, but across the top, we would choose right all the way. So while we've got some values and we're converging towards good values, it's important to note a weakness of linear Q function approximation here. In this cell here, we're told to go right. This is actually the weight that it's going to learn, and no matter how many episodes we're going to learn, this isn't going to learn anything better than going right into this wall. Why? Because the features that we've extracted are telling us that the distance in the x-axis and the y-axis are what's important. And this particular representation is ignoring the fact that there's a wall there. That's not part of our feature space. So our Q function will never learn that going right's not a good action. Similarly, we can see that the action of going right in this state, which leads us straight into the hole, is the best action. Again, this is because our features have nothing about this hole at all. The only features that we've got are how close we are to this green square. So if we wanted to improve this, we'd have to add a feature that effectively got us to move away from the -1 reward here in the whole. So these are okay, but one important property about linear Q-function approximation is that the Q-function is linear. If you're familiar with machine learning, you'll know that when we've got linear problems, the loss function is convex. Similarly here, although we don't have a loss function, we're trying to maximize the expected reward over all episodes, this is also a convex function. So therefore, the weights of our function will converge to the global optimum, rather than some local optimum. This is an important property of linear Q-function approximation, is the knowledge that we are always converging towards the global optimum. However, that's not the same thing as converging to an optimal Q-function. If our features are terrible, the Q values that it will learn will also be terrible, even though they will converge. So if we select poor features, we will get convergence on our Q function, but it might not be good. This illustrates the importance of feature extraction and good feature extraction for our problems. If we extract good features that represent the problem well, our Q function will converge to a good policy. Deep Q learning is another method for function approximation in reinforcement learning. In this case, the Q functions are represented using deep learning techniques rather than linear techniques. So instead of selecting features and training weights, we learn the parameters to a neural network. It's typical to use the notation QSA theta, where theta are the parameters that we're going to use. Note that in linear function approximation we also have the weights, but for some reason historically we don't usually add the parameter for the weights in linear Q function approximation. Using deep Q learning has the same benefits as using deep learning in other machine learning problems. First, it doesn't have the assumption of linearity between features such as linear Q function approximation does. And second, our input features can be unstructured, such as using images or text. This allows us to do things such as solve problems where the state space is a series of images rather than a set of table values. Deep Q learning is not particularly difficult compared to what we've already studied. In deep Q learning we do the same thing. Let's imagine that we have a Q learning algorithm. We execute a series of episodes and eventually we have to update the Q function. How do we do this? Well, our update to our Q function, QS of A, simply updates the weights of the parameters the same way we do in linear Q function approximation. Theta are our weights. So the update of our weights is the old weights that we have plus our learning rate multiplied by this new information. Looks quite similar, right? Our new information is the delta, which is our reward that we received plus our estimate for our future discounted reward. And instead of multiplying this by the feature value that we saw in linear Q learning, what we multiply it by is the gradient of the Q function at S of A. This character here, the upside down triangle, is the character we're going to use to represent the gradient of a function with respect to its parameters. We're not going to go into gradients right now, we'll talk more about that later. But for now what we have to just assume is that we take the direction, the gradient of this function here, and we update our weights in that direction. So as you can see here, deep Q learning is not particularly different from linear Q function approximation or even standard Q learning. All we're doing again is updating a set of parameters. Instead of being weights on a linear function, these are parameters to a neural network. And we update it the same way, multiplying our learning rate and our new information, and all we do is multiply it by the gradient at that particular point. This is very similar to linear Q learning, except it has the advantages of not assuming linearity between features and the ability to use unstructured input in our state, such as images and text. Now let's have a quick look at linear Q function approximation versus deep Q function approximation in the grid world example. So on the left we had the linear Q function approximation, on the right we have deep Q function approximation. The deep Q function approximation is implemented using PyTorch. The first thing to note is in the deep Q function approximation, parameters are randomly initialized, so it already looks like there are some weights trained, although this is still an arbitrary policy. We can step through the policy here and we can see in both cases the weights are getting updated, and early on the comparison is deep Q-learning still learning a good function as well as the linear Q-learning. If we just step through all of the episodes that we can train here, we go up to 30 episodes, we can see that both of them start to converge towards a good policy. There's not much difference here, but there's still a couple of things worth noting. Even the deep Q learning, despite not assuming linearity, it still learns a poor policy in some situations, such as it learns to go up into the hole here rather than go left and go around it. I'm sure if we tweaked the deep neural network, we might be able to get some improvement on this, but it would require quite a bit of knowledge about the problem and about how to learn these. The second thing is that the deep Q learning policy learns, approximations that are clearly wrong. There's no way we can ever get the reward of greater than 0 in this problem, so it's learnt this wrong thing here. So both of these learn reasonably good policies, not optimal policies, but they're good approximations that learn a lot quicker than the Q tables. The main difference between deep Q function approximation and linear Q function approximation is that deep Q function approximation doesn't give any guarantees on convergence. It can converge to a local optima, whereas linear Q learning is guaranteed to converge to a global optima. So now let's discuss the strengths and limitations of Q function approximations and the different ways we've looked at doing it. So Q function approximation compared to Q tables has a couple of benefits. The first is the compact representation it gives us. By this we just mean that it's much more compact to store a vector of weights or a vector of parameters than it is to store every state action pair that we do in a Q table. The second is Q value propagation. This just means that when we update the weights or the parameters of our approximation, that we update the Q values of multiple states in our MDP, not just the one state action pair that we've executed. However, Q function approximation also has some limitations. The first is that they're approximations. They only approximate the Q function that we're trying to learn. So convergence to an optimal policy is not guaranteed, although in linear Q function approximation, convergence to the global optimum is guaranteed for the features that we've selected. We can also compare linear versus deep learning approaches to Q function approximation. The first is that deep learning requires minimal feature engineering. This just means that rather than choose features, our deep learning system can often extract its own features. Also, the advantage of deep learning is unstructured input. But this would just mean that the states in our system could be images or unstructured text, and we don't have to format that in a way that's suitable for linear Q learning or Q tables. An advantage of linear Q function approximation over deep learning is the convergence property. That just means that linear Q function is guaranteed to converge to the global optimum, whereas deep learning will only converge to a local optimum in some cases. The disadvantage of deep learning is that it's a bit more data hungry. Typically requires more episodes to train than linear Q function approximation or other machine learning approximations. This is just because it learns the representation or the features as well as the parameters. In my own personal experience on some projects we've used reinforcement learning, I often find that deep reinforcement learning is overkill for a lot of problems, especially if you have any structure to your state spaces. When we're talking about very large state spaces and very complex systems, it's often easier to represent things by selecting some features and using those as abstract features for a Q table, or using machine learning techniques such as random forests to approximate your Q function. That said, there might be other people who are experts in deep reinforcement learning who might disagree here. But in my experience, often deep reinforcement learning is overkill. In this part, we looked at Q-function approximation. Using Q-function approximation, we can scale reinforcement learning techniques better by approximating Q-functions rather than storing complete Q tables. We looked at linear Q-function approximation, which uses simple linear methods in which we select features and then learn the weights for those features. And we showed that they can be effective and they have good convergence guarantees. We also looked at deep Q learning, which offers alternatives in which we don't need to select features and are more suitable for situations where our states might be unstructured, such as images. But it often requires more training data, that is more episodes, and has no convergence guarantees. Next, we're going to look at policy-based approaches to reinforcement learning. So stay tuned.